So welcome back, guys. We were discussing block equations, and we saw using block equations how to uh, look at the evolution of magnetization under different conditions. So we discussed one case where we discussed the evolution of magnetization under free precession, that is when we stopped the radio frequency pulse after bringing the magnetization down to transverse plane. What happens to magnetization, how it evolves back or relaxes back to thermal equilibrium, that is the z-axis. So let us write down the block equations once again. So we have mx, my, mz, then here we have minus r2 minus offset omega 1 sine phi, where phi is the phase of the pulse, RF pulse, offset, and R2 is the transverse relaxation rate constant, rate minus omega 1 cos phi minus omega 1 sine phi, omega 1 cos phi minus R1, and here you have mx, my, mz, and plus the R1 0 m0 part, right? So this is block equations. Now we saw the case of free precession where we saw that m plus of t is equal to m plus of 0, that is magnetization at any given point of time is equal to the starting magnetization multiplied by e to the power of I offset t and e minus t r2, right? This is the decay part of NMR signal, and this is the oscillatory part. So this is just to recap what we have learned earlier, and this whole thing is nothing but NMR signal, right? This is what it this term is what induces current in the coil when it is relaxing back. So this we have already learned. So now let us look at the effect of magnetization or effect of radio frequency pulse on to the magnetization. So let's see, case of RF field. So what happens to magnetization? How does magnetization evolve when you apply a RF field? So during RF field, relaxation effects can be ignored as they are too small compared to the duration of the pulse. So what I mean is, for a typical B1 field, let's say I'm applying a B1 field of 25 kilohertz, and my flip angle, let's say, is 90 degree. So typical t tau p, that is the pulse length, will be of microsecond time scale, so 10 microsecond roughly, right? Now this of course will also depend on the power of the pulse. So now T1 for a typical biomolecule like a protein or anything is of the order of 1 second, and T2 will be of the order of 500 millisecond, 300 to 500 milliseconds, right? So now within this short duration, the effect of transverse or the longitudinal relaxation will be very, very minimal. So hence from the above block equations, we can remove these R2 and R1 terms. So so basically the effect of relaxation during the pulse will be very, very small. So I must also mention that this discussion is true only for something called as hard pulse. So there can be two types of pulses. One is called as hard pulse, which is displayed like this, which is typically a high power pulse. That's why it is called as hard pulse, high power, and short duration. So because the duration is short, so you can ignore the relaxation effects. But the soft pulses can be drawn something like pictorially, something like this. So just to highlight that it's a low power and long duration pulses. So you cannot simply ignore relaxation effects in these so-called soft pulses. And we will not be discussing the effect of soft pulses onto the magnetization in this course. This is beyond the scope of this course, but if you want further reading, you are welcome to do so. So this discussion pertains only to the hard pulses where the duration is so short, of the order of microsecond, that the effect of relaxations can be ignored, and thus the modified block equations can be written as d by dt mx my mz, and you will have 0 on the diagonals, mx my mz, and plus the other term is also 0, which was r1 into 0 0 m0. Now your offset, let us assume for simple reasons, for make it simple, that the offset is also 0, so I'm going to put it 0 over here, and here what you are left with is sine phi minus omega 1 cos phi minus omega 1 sine phi and omega 1 cos phi. Now typical solution for these kind of equations. So again, we are not explicitly solving the equation, this block equation here, block equations here, but a typical solution, and actually you can go back and look at a few research articles where these equations have been explicitly solved both numerically and analytically. So this is out of, again, scope of this course, so I'm not going to go into the details of the solution, but we'll just discuss the final solution as such. So typical solution of these equations after integrating it between the limits 0 to tau p. Tau p is the duration of B1 field which is applied. So solution can be interpreted as overall rotation of magnetization about the B1 field. Okay, so what basically you're doing is by this multiplying this matrix and integrating this over the space from 0 to tau p, the overall effect of this on the magnetizations is that the magnetization is rotated about the B1 field. Magnetization is rotated about B1 field. What is the form of the rotation? So rotations are given as something like, so what we can show is m of tau p, that is the magnetization after application of B1 field for the duration of tau p is equal to, this is the starting magnetization, and then you have Rz minus phi Ry minus theta Rz alpha Ry theta again and Rz phi again. So typically what happens for all practical purposes, the offset is close to 0 and phase of the pulse is either along x or y, right? So let us only talk about Rz alpha, which is the rotation. So alpha is the flip angle over here. So which is the rotation about B1 field. So let us see how the what is the form of this matrix Rz. So these are matrices are called as rotation matrices. So now let's see how these rotation matrices look. So for Rz alpha, let us calculate for Rz alpha. Okay, how do you calculate that? Let's try to draw, because the rotation is about z-axis, so let's draw a two-dimensional coordinate system, because anything which is moving about z-axis, it is not going to change the coordinates of z-axis, right? So let's see, if you have a vector r which initially makes an angle p, let's say with y-axis, and it is then rotated to a new position. So let's say the initial coordinates are x1 y1, and then it is rotated to new position where it makes additional angle alpha. Okay, so it is rotated by an angle alpha, which is written over here, right? And the new coordinates of the vectors are now x2 y2. Okay, so now what I can do is I can write, so let us first write x1 y1 in terms of these angles. So x1 can be written as r, which is the length of this vector, cos p plus r sin p. No, sorry, what am I writing? So sorry about that. So x1 can be written as r cos p, that is this component over here, and y1 can be written as r sin p. Right? Now let us write the same way x2 and y2. So what is x2? X2 can now be written as r, because length of the vector is not changing, so that remains same. All you have done is rotated it about z-axis, right? So this will be r cos alpha plus p, and y2 can be written as r sin alpha plus p. So that is easy to see. All you are doing is taking the projections along x and y axis and defining those projections in terms of those angles, right? So for example, if I draw this, I can say that this length is x1, which is equal to r cos p, and similarly this length is r sin p, which is equal to y1. And then if you sum both these vectors, you will get this vector r, right? So if you sum both these components, vector sum. Now let's try to write x2 and y2 in terms of x1 and y1. So what do we get here? So x2 can be expanded as r cos alpha cos p minus r sin alpha sin p. Now I can write r cos p here as x1. So this is my x1 cos alpha, and similarly r sine p can be written as y1. So this is my y1 sine alpha. And similarly, let's expand y2. So y2 is equal to r sine alpha cos p plus r cos alpha sine p. So I've just expanded this over here. Now y2 can be written as, so if I replace r cos p with x1, so I got x1 sine alpha, and here I've got r sine p, so this becomes y1 sine p, right? Now I can write this in matrix form. So what I have got here is x1 cos alpha minus y1 sine alpha equals x2 x1 sine alpha plus y1, this will be alpha, sorry, and this will be cos, sorry about that. This is equal to y2. So what I can do is I can just convert this into matrix. So this is cos alpha minus sine alpha, and this is sine alpha cos alpha x1 y1. This is the initial position, and this is the final position of the vector x2 y2, right? So this is my rotation matrix. So this rotation matrix takes x1 y1 to x2 y2 from initial position to final position, and this rotation is in anti-clockwise direction, so that's why you have a negative sign here. If the rotation is done in clockwise direction, you will get a negative sign here instead of here, right? So that is very simple. So now this vector rz, because the rotation is about z axis, so I can write it as rz alpha can be written as cos alpha minus sine alpha cos alpha, and I can say that rest of the terms are 0 and z remains as z, so z coordinate does not change. If we now take it to 3 dimensions, so z coordinate does not change, so that's why there is a number 1 over here, right? Okay, so basically I can extend it as 0 0 1, and then if I do x1 y1 z1, this becomes x2 y2 z1, right? So if I take z1 over here, this remains as z1 because the rotation is about z1, right? So that coordinate will not change. Okay, so this is rz alpha, right? So similarly, you can alpha can be any angle, and the rotation is anti-clockwise. Okay, now similarly for, let's say, rx alpha, you can straight away write, now the rotation, if the rotation is about x-axis, so x will not change, and the columns and the corresponding row elements will be 0 0, and the whole block will come just like that, cos alpha minus sine alpha cos alpha. Similarly, ry alpha can also be written like that. Now y will be 1 and the corresponding rows and columns will be 0, and then you will be left with cos alpha minus sine alpha and cos alpha. You can explicitly do the same algebra here, simple maths, to see if what we have got is correct, but this is how it is done for Z axis I've shown, you can do it for X and Y axis, right? Okay, so now we have the rotation matrices. So now let us see how this rotation matrices affect the magnetization, right? So for, let's say during tau p, during 0 to tau p, alpha is 90 degree, pi by 2. So cos alpha terms will go to 0 and sin alpha will become 1. So I can say, and let's say if my B1 field is applied along x-axis, so then I'll have to calculate a rotation matrix for Rx, right? So my Rx alpha becomes this is 0. So 0, 0, minus 1, 0, 1, 0, 1, 0, 0, right? So now let's calculate. Now let's calculate the effect of rotation about B1 field, which is along x-axis, for a duration of tau p for alpha equal to 90 degree. Okay. I think I did some mistake in, let's see. Yeah. So this will be 1 over here, right? Let's rewrite this. So you have 1, 0, 0 here. So by mistake I wrote Ry alpha. Okay. So you have 1, 0, 0, 0, 0, cos alpha is 0, and sin alpha is minus 1, 1, and 0, right? Okay, so you have these three as values. Okay, now let's try to calculate the effect of rotation on the initial magnetization to final magnetization. Okay, so you have 1, 0, 0, 0, 0, minus 1, 0, 1, 0. Now let's say the initial magnetization is along z-axis. So how do you represent initial magnetization vector which is along z-axis? So there is no x component, so x component is 0. There is no y component, that is there is no transverse magnetization. All the magnetization is along z-axis. So I will write m0 here, or simply m I can write. Okay, so m is along z-axis, that means it is represented as 0, 0, m. So this is basically m k cap, initial magnetization. If the initial magnetization is, let's say, along x-axis, then you will write m0, 0, or if it is along y-axis, then you will write 0, m0. So for example, m I cap in vector form will be written as m0, 0, and m j cap in vector form will be written as 0, matrix form will be written as 0 and 0, right? Okay, so now this is simple. Now this is a 3 cross 3 matrix multiplying by 1 cross 3. So you can easily multiply and see what you get. So 1, 0, 0, so you will get 0 over here. So this into this, right? And then this into this. So here you will get minus m, and here you will get 0, right? So that means due to this rotation by Rx 90 degree, your Z magnetization has moved to minus Y, right? So negative sign, and it has gone to the second position, so that means the magnetization has gone to y-axis, negative y-axis. So what we have done here is, so if this is my magnetization and this is the direction of B1 field, and this will be my rotation. Okay. So new magnetization is along this axis. This is effectively what we have done. So Rx is the rotation about this rotation, anti-clockwise rotation about x-axis, and thus mz, the magnetization along z, which was initially there, it moves towards minus y-axis onto y-axis, and if the flip angle is 90 degree, it will land at minus y. Okay, right. So this is very simple. So now we have seen that how the block equations actually can show you the evolution of magnetization under free precession as well as under effect of hard pulse or radio frequency field, RF field, right? So let's do a simple exercise. So I would give you a small home exercise that you can, so that you can follow today's class. So let's say if you have starting magnetization of mx, my, mz. Let's say you have all three cases, and the pulse which you are applying is, let me write it clearly. Okay. So the pulse which you are applying is, let's say here you have 30 degree x pulse. Then you also have, let's say, 45 degree y pulse and 90 degree z pulse. So what is the outcome of magnetization in all these cases? So you should be able to calculate that now. Similarly for y, let's take the same angles. What happens to y? 30 degree x, 45 degree y, 90 degree z. So please calculate these rotations and see what is happening to the magnetization. You can also do a little complicated case. I mean, not complicated, but let's see what you get if you do a 90 degree y plus 90 degree z rotation. Okay, so what happens that? So back to back two pulses are applied with different phases. Okay, so try to work out and try to play around with these matrix rotations so that you know how do you choreograph the magnetization or how do you choreograph the spins by varying different type of RF fields. So by applying different type of RF fields, you can actually take the magnetization to anywhere in three-dimensional coordinate frame, and you accordingly you can perturb the signal, or accordingly you can actually change the starting signal. So this is routinely done in different type of NMR experiments, where sometimes we have to throw a pulse which is 45 degree of in angle, sometimes we throw a pulse of 30 degree angle and 90 degree. So all of these have different uses in different experiments. We'll learn later, but you should know how to apply these pulses, and you should know what is the effect of these pulses given a particular starting magnetization. Okay, all right. I think that is all for today. See you in next class.